Hello, my smart and talented friends, and welcome to the Global Science Network. I have been making lots of progress on building a 4-bit computer using individual transistors. This is big news because this video is going to be super interesting as it really shows you how a computer works. This should get you excited about electrical engineering projects in such a way that we can work together to build artificial neurons, non-biological life, and ultimately create non-biological human consciousness. Everyone should know how to build a computer at the transistor level, so please share this video. This may look complicated at first, but if you break it down into individual sections, it is actually quite simple. I do recommend watching my other videos on how to build digital logic gates, data flip-flops, and how computers add numbers. If you have watched those videos, this video will make a lot more sense. Even if you do not understand exactly what is going on in this video, I still recommend watching it until the end, as some parts are easier to follow than others. The computer is built on breadboards. The circuits that we have built include the clock, data bus, 10 bytes of memory, the accumulator register, B register, ALU, and output register. I am going to start out by talking about how the computer is built. Then we will run an example program, followed by having the computer continuously add to, and then continuously subtract to. By the end of the video, you should have a good idea how a computer actually works. Let's get to it. This diagram here shows how this computer is built. Each one of these blocks represents a breadboard. So the computer is 8 breadboards tall, 2 breadboards wide, and then we have a data bus and a clock. These arrows represent how the information is flowing around the computer. So our clock signal gets put onto the data bus, the output from our memory gets put onto the data bus, and then for the A register, information can be put onto the data bus and it can also be received from the data bus. The accumulator register also sends information into the ALU. Register B has information come from the data bus, and then once it gets latched, it gets sent into these ALU XOR subtract gates, and then that information, once it's done processing, is continually being sent into this part of the ALU as well. So for the ALU, we have a 4-bit input coming from the A register, and then we have a 4-bit input coming from the B register. Once the ALU is done making the calculation, it gets sent out to the data bus via the ALU tri-state buffers. And then finally, the information from the ALU will be put onto the data bus, or the information that's located in the accumulator register will be put onto the data bus, and then this information will get latched into the output register. The data bus has 8 columns, which are 0 volts, 5 volts, clock, clear, and then our 4 data lines. All right, now let's talk about how this computer is built. If we go to the top left corner of the computer, we will see the clock, and the clock is located right here. And this is just an astable multi-vibrator. It's pretty basic, and we have talked about this in other videos, so I'm not going to go into too much detail with that. Also at the top of the computer, we have these 2 breadboards of memory. So if we come over here and we look at our computer, this breadboard of memory has 4 bytes, and this breadboard of memory has 6 bytes. And how this basically works is these are actually simplified tri-state buffers. And if you look right here, this is byte 1, and it's made with 4 bits. So this is bit 1, bit 2, bit 3, bit 4. And then all together we have 10 bytes. So this is byte 1, and then 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if we actually just look at byte 1, we can see that these resistors, depending if they're in positive or negative, will determine if the value is on or off. So we can see that these values are on, and off. But whenever it gets sent out, this is actually going to be a 0001, or the value of 1. So you can just set all of these values, and then the enable pin is actually connected via these red wires. So we can actually just enable which one gets sent out to the data bus by flipping these switches for the first 3 bytes. If you actually look close at how this memory module is built, there actually is quite a bit of wiring involved, and I'll probably make a separate video explaining exactly how to build this, but for now, that just gives you a general idea how our memory module is built. Next, let's look at the accumulator register, and this actually takes 5 breadboards to build. So we have 1, 2, 3, 4, and 5. And this is actually the first register that I built to hook up to the data bus. So if we look at how this is built, the top breadboard actually contains the tri-state buffers, and then the next 4 contain master-slave data flip-flops. So if we go over here to our actual computer, right here we have the tri-state buffers, and this is the master-slave data flip-flop number 1, and then number 2, number 3, and number 4. When looking at the accumulator register, we actually have data that can be sent from the A register to the data bus via these tri-state buffers, which are connected using these yellow wires. And then we actually have information that can come from the data bus to the A register, which is connected with these red wires right here. And then the clock is connected into our clock gate, which is right here. And we actually do have buffers going into each data flip-flop. And this makes it so that it can properly be connected to the data bus. And then finally, we have information that is sent out of the A register and into the ALU by going through these blue wires and then down into these red wires, which connects directly into the ALU. Again, I will probably make a separate video explaining exactly how to build this accumulator register, but it's actually a really important one to know how to build. And it's a good one to build to get the data bus working properly. So next, let's talk about the data bus. So if we look right here, we can see that lots of different registers are going to and from the data bus. So if we look right here, the data bus runs pretty much the entire height of the computer. And by default, the value of the data bus is actually on. So if we actually look right here, these LEDs represent the value of the 4 data columns. And right now they are all set to on. They are all set to on because if we look up here, we actually have pull-up resistors right here. These pull-up resistors connect from positive and they go into each one of these columns. So by default, the data bus is on. And you might think that whenever you're actually sending information to the data bus, you would be sending a positive voltage. But what's actually happening is whenever you want to turn something off, you actually just provide a path to ground for these pull-up resistors, and then that makes the value on the data bus off. Also, if you look at the wire colors, white just means that power is going to be sent. So we distribute the power around the computer using the white wires, so you can pretty much just ignore those. If information is being sent to the data bus, the wire is usually yellow, and then if we're sending information from the data bus to the other registers, we will use a red wire. Register B is built on 2 breadboards, and each breadboard contains 2 data flip-flops. These are not master-slave data flip-flops, they're just regular data flip-flops. So if we come over here, this is register B, and we can see that this is data flip-flop 1, 2, 3, and 4. And if you look right here is a clock gate, and then we do have buffers going into each one of the data flip-flops. The data comes into the B register from these red wires right here, and that will turn the value on or off. The display for the B register can be seen right here, and the display for the A register can be seen right here. And this is actually really nice because whenever we're trying to determine what the value of the ALU is, it's going to be A plus B or A minus B. So this is actually a really good way to display how the computer is working. And once the data comes into our B register and gets latched in our data flip-flops, it actually instantly gets sent to our exclusive OR gate board right here. If this is enabled, it will change the value, and if it's not enabled, it will just pass through this board and then go into the full adder part of our ALU. So if we look right here, we can see that we have register A and register B being fed into our ALU, which is what we want. Next, let's talk about our ALU. We can see that it is built on 5 breadboards, and at the top of the ALU, we have our XOR subtract gates. So if we look over here, this right here is our XOR subtract gates, and what this does is it makes it so that the computer can subtract. The data will either just get passed through this, or if it's on, it will actually make the 2's complement of whatever value is being sent in by the B register. So we have some buffers on the left side, and then we have 4 exclusive OR gates. And that will allow the computer to subtract. And then if we look, we actually have 4 full adders. So on one breadboard we have a full adder, and then on this breadboard we have a full adder, and on this breadboard we have 2 full adders. So if we go over to our computer, this is a full adder, this is a full adder, and then this is 2 full adders. And then finally at the very bottom of the ALU we have our tri-state buffers. So if we look right here, here are the tri-state buffers for the ALU. So if we want to send data to the data bus, it's going to be done through these tri-state buffers. And if we look using these yellow wires, it does connect to the data bus. And finally, we have our output register, which is built on 2 breadboards, and each breadboard contains 2 data flip-flops. So this register is actually built very similar to register B. So if we look right here, we have 4 data flip-flops, 1, 2, 3, and 4. And then at the left side of this register, we have some buffers, buffer. This is the clock gate, which is actually just an AND gate. And then we have another buffer right here, which is connected to the clear pin on our data bus. So if we want to reset this to 0, all we have to do is ground this value, and our output register will be cleared to 0. All right, I am going to power up this computer, and we are going to run this example program. The first thing we are going to do is load A with a value of 1, and then we are going to add 2, add 2, add 2, subtract the value of 3, and then output a value of 4. All right, the first thing we want to do is load the A register with a value of 1. The value of 1 is actually located in our first byte of memory, which we will send to the data bus by flipping the switch right here. So now we have a value of 1 on the data bus. Now we are going to send this value into register A by flipping this switch right here. So now we have a 1 on the data bus. We'll flip this back, and then we'll flip this switch right here so that we no longer have data being sent from memory to the data bus. And now our load A command is complete. The next thing we want to do is we want to add 2. So we want to send 2 to the data bus, which we'll do by flipping this switch right here. Now we have a 2 on the data bus, and we want to send that to register B, which we can do by flipping this switch right here. So now we have a 2 in register B. We'll flip this switch so we no longer have data being sent from memory to the data bus. And now we have 1 plus 2 equals 3. So the value in our ALU is 3, and we can send this to the data bus through these tri-state buffers by flipping this switch right here. So now we have a value of 3 on the data bus, and now we want to load that into the accumulator register. So we can do that by flipping this switch. But we actually have to flip this switch pretty quickly because the A register is actually connected directly to the ALU, so it will update this value and then send it back to the data bus. So we can actually only have this be on for 1 clock pulse. So I will flip this back and forth very quickly, and now you can see that we have 3 in the A register, which is what we want. Now we will turn off these tri-state buffers from being able to be sent to the data bus, and we are going to go to the next command. So the first add command is complete, and now we need to do the second add command. So we will send the value of 2 to the data bus, and we will load it into the A register. This is kind of redundant because it's already there. And then we will turn off the memory from being sent to the data bus. And now we have a value of 3 plus 2 equals 5. And we're going to send this value of 5 to the data bus by enabling these tri-state buffers. And now this value of 5 that's on the data bus needs to be loaded into the A register. So we will flip this switch very quickly. And now we have a value of 5 in our A register. So we will turn off our tri-state buffers from being sent to the data bus. And now our second add command is complete. So we will do the same thing the third time. We will have our memory connect to the data bus. So it's connected to the data bus, and we need to load it into register B, which we can do right here. It's already loaded, so that's good. So now we have a value of 5 plus 2 equals 7, and we need to send this to the data bus, but we actually forgot to make it so that our memory is no longer connected to the data bus. So we have to flip this switch first, and then we'll make it so that the ALU is connected to the data bus by flipping this switch here. And now we have a value of 7 on the data bus, which we're going to load into register A by flipping this very quickly. And now we have a 7 in our A register. So we will make it so that this is no longer connected to the data bus. And now all of our add commands are complete. Next, we're going to do a subtract. So this one is going to be different. This time we're going to use the third value in our memory. So now we have a value of 3 on our data bus. And we're going to load that into the B register. And then we're going to turn this off so it's no longer connected. So now you can see that we have 7 plus 3 equals 10. But we actually want to subtract 3, not add 3. So we're going to flip this right here so that it actually runs through our exclusive OR gates. So whenever we flip this, now we're actually doing subtract. So we have 7 minus 3 equals 4. So this value is 4 right here. You can see that we actually have this blue light also enabled, which is our carry bit, but that's actually what we expect whenever we're doing a subtract command. It's perfectly fine. The only thing that's going to be sent to our data bus is the value of 4. So whenever we enable this here, now we have a value of 4 being sent to the data bus. And this was actually the last command that we needed to run in our program. So we can actually send this to the output. And we also want to send it to the A register. So we can do that real quick as well. So now we have a 4 in the A register, a 4 in the output register. We do want to make it so that the output of the ALU is no longer being sent to the data bus. And now our program is complete. So the computer is halted. Technically, we would have to change it so that the program counter and the ring counter are no longer incrementing, but we don't have that in this case. So our program is done. Now, technically, we wouldn't have actually wanted to send the output directly into the output register from the output of the ALU. You would actually want to load it into the A register and then load it into the output register. So let's clear the value of the output register and do that last step that way. So we can actually clear the output register by just having the clear pin go to ground. So I'm going to connect clear to ground, which is actually this 4th pin right here. So now our output register is cleared. So now we need to get the value from our A register. And we don't actually have the output from these tri-state buffers hooked up to a switch, but we can make it so that this resistor, rather than being connected to positive, goes to ground, which will send the output from this A register to the data bus. So let's do that real quick. Instead of being positive, we will send it to ground. So now we have the value of 4 on our bus, and we were going to send that to the output register. So now our output is proper, and then we just need to put this resistor back into positive so that the A register is no longer outputting to the data bus. And now our program is actually completed the right way. We wanted an output value of 4, and we have the output value of 4. All right, I'm going to power up this computer, and I'm going to make it so that it increments by 2. And in order to do that, the first thing we need to do is have the value of 2 be sent from memory to the data bus. So I know that it's actually, the value of 2 is actually in the second memory location. So I'll flip this switch. We have a 2 on the data bus. We need to send that to the B register, which we can do by flipping the switch right here. So now we have a 2 in the B register. We want to make it so that our memory is no longer connected to the data bus. So we will turn this off. And now we actually want the ALU to be continuously connected to the data bus. So we will actually flip this switch right here to do that. And now we want the data bus to be continuously connected to register A. So we can do that by flipping this switch right here. So now our computer is actually incrementing by 2. I also want to show this output in our output register, so I'll flip this switch right here. And now we can see that the computer is counting by 2. Next time it resets, I'll count. So we have 2, 4, 6, 8, 10, 12, 14, off, 2, 4. So now this is just going to continuously add by 2, but we can also have it subtract by 2. If we flip this switch right here, which enables our exclusive OR gates, it will actually be counting backwards. So let's do that. So now our computer is actually counting backwards, and next time it resets, I'll count. 14, 12, 10, 8, 6, 4, 2, off, 14, and then it's just going to continuously keep counting backwards. Now, in order to make it so that the computer is no longer looping, we need to make it so that the output of the ALU is no longer connected to the data bus. So we will turn this off, and then we'll make it so that the A register is also not connected to the data bus. So we will turn this off, and we'll make it so that our output register is no longer connected. So now the computer is officially halted, and the program is complete. To power this computer, we are just using this 5-volt battery pack right here. And you also might have noticed on the power rails we have a bunch of capacitors. These are 10 microfarad capacitors, and it just makes it so that if there's any voltage fluctuations while the computer is operating, it will make those nice and smooth so the computer does not run erratically. Right now the computer is using 0.57 amps at 5 volts. Whenever the computer is completely finished, I want it to use less than 1 amp, so it seems like we're doing pretty good. There's actually quite a few things we could do to make this more power efficient, but it doesn't look like I'm going to have to do too much extra work in that regard. Now, we did set up the example program this way for a specific reason. Load, add, subtract, output, and halt are actually called opcodes, and we're actually going to be able to store 7 opcodes in our program memory. And we're also going to be able to store 3 values. So we're going to store a specific value for load, add, and subtract. So this is the tentative configuration of the completed computer. Right now we have this half of the computer built, the data bus, and the clock. But we still need to build the opcode register, the opcode decoder, the control matrix, the program counter, and the ring counter. Now this half of the computer really controls the timing of when these registers on this side of the computer get enabled and when information is supposed to be sent all around the computer. And I actually have a lot to say about how this is going to be built, but we're going to build it and talk about it in the next videos. So if you want to watch the next video where we build the second half of the computer, click right here.